Okay, here's the second application I'd like us to look at, and it's the double spring mass system. So we looked at this in module 3. So remember what we've got. We've got two masses and two springs, and right, there's a spring between mass C and the wall, and there's spring B between mass C and mass D. So we're going to let the spring constants all equal 1 and the masses all equal to 1. So this gives us a four-dimensional homogeneous linear system, right, where x1 and x2 are the positions of the masses and x3 and x4 are their velocities. And so we get those equations, right? So x1 prime equals x3 and x2 prime equals x4 because x3 and x4 are the velocities. And then by looking at how the springs act on the masses, we get x3 prime equals x2 minus 2x1, x4 prime equals x1 minus x2. So this is a 4x4 matrix. And so let's look at the initial value problem where mass D is fixed initially. We take mass C and move it to the left 1 unit, and then we let go of them both simultaneously, and they're going to start moving away. So we want to figure out what that is. Okay, so we want to use maxima to find the general solution. So we know what to do. We take that system of equations and we turn it into a matrix. And there's our matrix A, right? So double check that the equation before gives us this matrix. We then ask maxima to find the eigenpairs, and we'll give it to us as numbers, okay, as decimals. And this is our output, and it looks pretty daunting. Up there, we see our matrix A, and there's our eigen values, and it's looking pretty complicated. Oh, firstly, notice that all the eigenvalues are purely imaginary, and we expected that, right, because there's no damping in this system. Okay, so we're expecting some kind of harmonic motion. Now, those numbers are really hard, square root of 3 minus square root of, 3 minus square root of 5, the square root of that divided by square root of 2. Way too complicated. But when we look at them as numbers, actually we recognize what it is, because that's just the golden ratio. And you can actually see somewhere, golden, it actually gives square root of 5 plus 1 divided by 2. That's the golden ratio. Okay, and if you want a nice little algebra exercise, prove that those square roots of square roots actually is the golden ratio. It's not that hard. Anyway, don't bother about doing that, but that's just what it is. So that means our solution is actually nicer than we deserve it to be, right? The second vector there is 1, 1, 1, 1. That's telling us that everything has multiplicity 1 eigenvalue. So great, we've got a full set of eigen vectors now. And then we see, again, now we see the eigenvectors there, again with the initial place being 1. That's the standard thing that maxima does. If you look at the textbook gives it in a more general form, and it doesn't recognize it's the golden ratio in place because they didn't actually look at the decimal numbers. Okay, so if you remember the golden ratio, 1 minus the golden ratio is actually the inverse of the golden ratio. So I just let A be the inverse of the golden ratio, that 0.6180339, blah, blah, blah. And we can just read off this off the general solution, right? Because it's purely imaginary, there's no exponentials, okay? And by the way that the eigenvectors is set up, we phase out the, sift out the real and the imaginary, and we can decipher it to be x1 is c1 cos at, etc. And then x2, so the natural frequencies of this system are a and 1 plus a. Okay, and we've actually solved that problem. Okay, so next we want to find the initial value problem. Okay, so if we go back and plug in t equals 0, we see that, you see what our matrix B is, that we multiply the C, the constant vector, the constants of integration vector. So we invert that matrix and we multiply it by our vector of initial values, which is -1, 0, 0, 0. It could be whatever we want. And when we do C times V, that actually gives us our constants. And so there it is there. So B is our matrix when we plug in t equals 0. C is that inverted. It's 0.27 something and 0.44 and 0.72. You could actually probably figure out what that is in terms of the golden ratio. I didn't bother doing that. And we multiply it by our vector of initial values, and we see that C2 and C4 is 0, and so the functions just cos functions are involved. And actually, if you do again, if you actually do the numerical computation, when you go back and you figure out C3 times A, it turns out to be the same as C1 times 1 plus A, which again is kind of not obvious, but anyway, there it is. And so then we want to print it. And so there's our solution. So x1 and x2 are the positions of the springs, remember, and x3 and x4 is just the derivative of that thing. And then I just plot x1 and x2, and I tell Maxima what the value of those parameters are. And there we go. And there's the fun and games of how the springs jostle back and forth. Okay, and that's it. Oh, for homework, I'm giving you a similar problem to solve. A different setup of springs. It's actually the one that was given in exercise 12 in section 4.1. I'll actually later on in the week actually post the solution to that so that you start off at the right point. And we'll see what solutions you get. Okay.